Today we're going to see some examples as they apply the laws of motion to vehicles and to the definition of velocity and acceleration, which are the ones that originate the equations of motion. So let's look at some detailed examples as they apply to vehicles and they make more sense of the equations. So let's see here. I'm gonna disappear from here. We're gonna look at in here. It says the following. You have this vehicle. Alright. It moves in a straight line such that for the short time the velocity is defined as v equals to 3t squared plus 2t in feet per second, where t is in seconds. Question is determine its position and acceleration when t is 3 seconds and when t is equal to 1 second s equals to 1 second. So let's just look at the solutions in here, which illustrate the very basic concepts. The position coordinate extends from the fixed origin to the vehicle. So we have this S coordinate in here. Since the velocity is a function of time, the car can be determined by v is ds dt. Since this equation relates to Vs and t, in this case, when t is 0, s is 0. So the velocity is 3t squared plus 2t. If you're going to find the position, you integrate the velocity on both sides from 0 to t, and so you're gonna have a result of the integration from 0 to t. So it's 3t squared plus 2t squared. So you're integrating now is yeah. And then you have that s is t cubic plus t squared. So when you have t equals to 3 seconds, then the position would be 3 feet, 36 feet. The acceleration, knowing the velocity is a function of time, acceleration is determined by dv dt. So in this case, you have that the velocity is given to you, but you're going to calculate the acceleration. Acceleration is the derivative of the velocity. So you weigh 6t plus 2 when t equals to 3 seconds. This is an interesting observation in here, that the formulas for constant acceleration cannot be used on this because the acceleration is a function of time. So it all depends on the motion. So it all depends on the motion in this case, because the acceleration is a function of time and we have to differentiate, then we have to use its own equation and not the equation of linearly accelerated motion, which is the basic equations that we know of. Here an observation. The same results can be obtained by evaluating a constant of integration rather than using definite limits on the integral. For example, if you integrate ds is 3t squared plus 2t dt, you will obtain that s squared is t cubic plus t squared plus c. So if you use this condition when t is 0, then c is 0. Okay, so that is a short application of this. Let's look at this example now. It says a bicycle moves along a straight road such that its position is described by this graph that is shown in figure 12.9a. Construct the velocity time and acceleration time graphs for t equals to between 0 and 30 seconds. So you have this data that you're giving. So the bicycle is moving this way, and what you see is that it has some sort of a parabolic motion from 0 to 10 seconds. Probably he's accelerating in there, changing rapidly. And then over here, the change in the velocity is a constant. So you can see that in here is asking us to consider that this is a function of like a parabola that says that s is equals to t squared, and then the one over here is a straight line. So let's just look at this solution here. Since the velocity is ds dt, then the velocity time diagram can be determined by the differentiating the equations that define s. So if you have the case that s is equal to t squared over here, that's the motion here. The velocity is going to be 2t. So, but after 10 seconds and less than 30 seconds, that s is 20t minus 100. So what I'm trying to say is that in many problems we might know just pieces of the motion, and depending on what we know, we will apply the equations. Like in this case, we have the combination of a set of two types of motion, one in a parallel I'm gonna say parabolic motion, and the other one in rectilinear motion. Okay. Let's take a look at this one. This one has a different kind of situation. In this case, you have that in this figure, you have a vehicle that starts from rest and travels along a straight track such that it accelerates at a constant rate of 10s and then decelerates at a constant rate. Draw the velocity and time and the position versus time graphs and determine the time t prime needed to stop the car. So how far would the car have traveled? See, this is very important because in accident reconstruction, you have to start with what you have, with the evidence you have. And many times you have to decompose the motion as this problem has to be able to do that. So let's take a look in here. This is the time and this is the acceleration diagram. Yeah. And in the graph, if you have a velocity and time diagram, since the velocity is the dv is the acceleration times dt, then the velocity time diagram could be determined by integrating the straight line segments of the acceleration graph using the initial condition p is 0 when t is equal to 0. So in this case, you have that the acceleration is, that the velocity is the integral of the acceleration. So you will have that the velocity is 10t. When t is equal to 10 seconds, the velocity is 10 by 10, so it's 100 meters per second. And using this as the initial condition for the next period, you have that if a is equal to -2, the integral between 0 and 100 is -2, and the velocity is minus 2t plus 120. Okay, so this is just consider experimentally what has gone on with the motion of a vehicle as opposed to just strictly applying those equations. Now, this is the diagram of the velocity versus time. If we want the diagram of the position versus time, then we have a different story. And here, if you integrate the equations that ds is equal to dv dt, so position is the derivative of velocity is what it's saying here. But if you integrate the equation for bt, it will yield the equation st. And we use the initial condition for s equal to 0 and t equal to 0. So between 0 and 10 seconds, which is this one here, so if you have b is 10t and you have 0 to 10, to get the position you have, this would be 10 times dt. So when t is equal to 10 seconds, S is going to be 500 feet. 5 times 10 to the second using this initial condition. And then when you have from 0 to 60, B is equal to minus 2t plus 120. Okay, so in here you will know the position as being minus 500. That's equal to t minus t squared plus 120 plus 10 squared minus 120 times 10. So from here you'll know you have S. So let's examine what happens when the time is 60 seconds. So you have an initial parabolic curve here, and you have over here and another one. Okay, so you have this is that the position here is minus t cubic plus 12 times this substituting in here, you know that S is equal to t squared plus 12r minus 600 if you keep if you add everything. Now in this case, if t prime is 60 seconds, which is part of what the problem is asking, what's the position? So you see, and that's the case, you have this parabolic side and you have this rectilinear side. Well, it's not really rectilinear, it's another quadratic equation. So it says, note the direct solution for S is possible when t prime is 60 seconds, since the triangular area under the VT graph would yield a displacement delta S minus 0 from t is equal to 0 to t star. And so delta S would be 1/2 of 60 plus, so this is 3,000 meters. So let's go take a look at another one. Okay, so let's take a look at this example now, the example the 12.8 in here, and you have this diagram, and describes the motion of this motorcycle, and is shown on this figure. It says construct the acceleration position graph of the motion and determine the time needed for the motorcycle to reach the position of 400 feet. Okay, so if you have this graph that you have measured, or you know it's like this, to reach it accelerates and then it goes at a constant level here, the velocity, for 200 seconds. So it basically acquires the velocity and then is just coasting. So and here you have, since the equations for the segments of the velocity position graphs are given, then the acceleration position graph can be determined by using the fact that the distance is the velocity times dv. Okay, so in this case you have v, which it would be 2s plus 10, like this, and then the acceleration would be v times dv ds. Okay, so you have basically two sections, one from 0 to 200 feet, and the other one from 200 feet to 400 feet. And then you have this velocity is constant. So in here you use the acceleration as v dv ds, and v is 50 times dv ds, d of 50 ds is equal to 0. Yeah. So the results are plotted on this, the next one. The time can be obtained using the v and s graph and vs ds dt, because of this equation relates to v, s, and t. So if we look at this in here, we will see that if you do the integration on both sides here, t is 5 times natural log of 0.2 s plus 10 minus 5 inches. And so at s is equal to 200 feet, t is 5 inches, and then 5 natural log of 0.2 times 200, and then we continue with this until we get 0.05 s. Therefore, for the second segment of the motion, you have this, where v is 50, and if you integrate it in time, you should be able to come up with the answer that the time is going to be 12 times this. So this is the other thing. If you have this graph like this is how the velocity was changing at first, and then it went in constant velocity. So when we're analyzing a crash of a car, as I mentioned, it's being important to do the analysis of the motion in this kind of plots. and you can get some nice answers from this. So in here you have you can check, it says the results by calculating the slopes. So for example, from S equals 0, A is BdV, so equals to 10 times 50 minus 10 divided by 200, it would be 2 meters per second square. Of course, you can inspect the graph. The BS graph indicates an initial increase in the velocity followed by a constant velocity. So if you do these graphs, they can be very useful and get you more information of what we needed to know. We need to know the acceleration, but mainly the velocity and the position. Those are the two things that are crucial. So when there is a vehicle collision, the position is very important and often determines how the how often determines, and you can do an investigation to see how it fits with the situation.